All right, welcome back here to homework 2 this time, part 1, and I'll be working through it here. This time around, it will be a mix of both deriving and coding. And so I have my typical phone cam, and I have a different angle this time to sort of show what's going on my monitors and sort of workspace. All right, so let's read it out here. So a sealed cylindrical tank with height 1 meter and cross-sectional area of 1 meter squared is filled with uh, to a initial height of zero point 0.9 meters with water. The headspace above the water was initially atmospheric, or 101,325 pascals. A hole of size 0.001 meters squared is punctured at the bottom and the water drains out. So derive a differential equation for solving the height of the water in the tank as a function of time. So that's, I guess, part one of part one. This next part is the coding portion. So solve the problem numerically and plot your results using scipy integrate, solve IVP and plotly respectively. To avoid round-off errors arising from simulation times extending beyond the steady state reached by the system, and use the events feature to terminate the solution when the calculated velocity of the exiting water reaches 0. All right, so it doesn't seem too bad, so I'll move that up. And so let's start with part one of part one. So let's draw out our situation here. So sealed cylindrical tank. Pretend that's touching. With a cross-sectional area of AC, total height of H, uh, initial height of water of HI. We have a hole at the bottom, just small enough to where only the fluid flows out and air isn't able to get back in. Um, we know that the headspace has the initial pressure of atmospheric. That will come in handy later. And so that's about it for what we can draw, right? Well, we have a bunch of givens, but it won't really help us by drawing them out here. So this problem is sort of applying a concept that I had learned, and that is sort of using Bernoulli's equation. And so let's sort of apply Bernoulli's equation for this problem. So what is Bernoulli's equation? Well, it's the pressure difference divided by rho at two selected points. All right. Then it's the velocity squared difference uh, divided by 2. So the velocity squared at point 2 minus the velocity squared at point 1 plus the uh, uh, height difference. So this deals with the energy within the system. All right. So if you haven't already guessed, kinetic potential, the sort of uh, this is a complicated term, so I won't go too much into it. But pressure difference deals with the simplification of uh, injection work, enthalpy, that type of stuff. So anyway, so then this is all equal to the frictional heating. So, and then there would be non-flow work, but there's no stir or anything inside that, so it will just be frictional heating on this red side. And so let's sort of discuss. Let's start the variables within this equation. All right. So for Bernoulli's equation, right, we have to select two different points. And well, if we want to solve for the, I guess, the flow rate coming out of the tank, right? Well, we would obviously choose right at the hole as one of the points, and then the other point I'm going to select here is the surface of the water. So this is point 2, and this is point 1. And so let's start discussing the pressure, the velocity, and the heights, I guess, and, well, the frictional heating as well, later on, for these 2 points. Well, for point 2 here, what is the pressure? Well, uh, going out from this hole, we can see that the area uh, sort of is a sudden expansion, right? The area is sort of infinite in a way. And because of that, there would be no pressure recovery. And by saying that, we can also say that the pressure out here, atmospheric, so I'll label this as P external, these pressure at 2 will be equal to that pressure external because of the sudden expansion. And also because of that, since we're saying that the 2 pressures are equal at the hole, directly right at the hole, we sort of account for the frictional heating. And so the frictional heating for this area, for that, would be 0. Since we're already talking about frictional heating here, let's also discuss the frictional heating from point 1 to point 2. What we're actually going to do is sort of approximate that as 0. In reality, there probably would be a very tiny bit of frictional heating as the water is flowing from point 1 to point 2, but for our purposes, it can be approximated as 0. So ultimately, this frictional heating will be 0. All right, so that's out of the way. And we just now discussed that the pressure at point 2 will be equal to the external pressure, which will be atmospheric. Moving on to the pressure at point 1. Well, we know that initially in that headspace it was atmospheric, and well, the pressure at that height, since I labeled it as the surface of the water, it will also be equaling that pressure. And then, well, since it's a sealed container, and well, we punctured a hole, it'll be flowing out, and so the volume of that headspace will be increasing, thus decreasing the pressure. And so now we've sort of figured out that this pressure 1, at point 1, has some relationship with the height, and ultimately time as well. And so we'll sort of figure that out in a bit here. The velocity at point 2, well, that's what we're solving for. So we'll move on next to velocity at 1. Well, with respect to the velocity at 2, this velocity here is sort of basically 0, right? It's not really moving, you could say. So I'll sort of list out what we've been discussing. So we will say that, and then V1 is basically 0. It isn't really moving at that point. Next, potential energy. Well, we've denoted G as positive in the downward direction. So positive in the downward direction. And so now, where would we sort of put our baseline, I guess, where was our 0 to calculate our heights from? And well, you might already notice what I've done on the left here. It wouldn't make sense. I've already sort of implicitly implied that I would put 0, our baseline, as the bottom of the container. And well, it wouldn't make sense to make our 0 the height of the water, right? The surface of the water. Because like I said earlier, for the pressure, it's flowing out, right? So this surface of the water is decreasing. And so our baseline would be decreasing, which would then make our calculations a lot harder. And so we've made our baseline the bottom of the container. And so Z1 is decreasing. And since it's going from final to initial here, the H is going away from the positive direction, and thus being negative. We'll have a negative height every time, because it will be 0 minus whatever height, right? So 0 minus H is negative H. And so ultimately our potential energy term just becomes, I'll write it up here. a potential energy term ultimately becomes just negative GH, since Z2 will always be 0. And so that deals with most of the other terms. So now we can sort of go back to the pressure at point 1. So like I said, it is changing. And well, the only thing, well, not the only thing, one of the things that are constant throughout that is the moles of gas. And why do we need the moles of gas specifically? Well, we want to solve for the pressure at point 1, right? And well, we're going to also say that the gas in this headspace is ideal. So we can use ideal gas law. Is equal to nRT. And so, well, we can solve for everything. Well, P1's changing, V is changing, and well, R and T, we'll just keep that constant. So we'll need the moles of gas initially, because that will stay constant, whether or not it's changing. So that's why we have to solve specifically for the moles of gas. And so when we do that, I'll just write on this side here. The moles initially will be the pressure initially, right? Times the volume initially over RT. And so then if we, let's sub that in now to the pressure and solving for the pressure 1 at point 1, we'll get pressure initial, volume initial, RT over the volume, and then RT. So those RTs cancel, and we get the pressure at point 1 is equal to pressure initial times the ratio of volumes. And well, we can also solve for these volumes, right? Because we're given the cross-sectional area and we have heights. So what is the volume initially? The volume initially is going to be that cross-sectional area times the height of that headspace, which would be calculated by, oh well, the height of the liquid initially. My bad. Yes, the height of the headspace initially. So H, big H minus H initial. And then the volume will be calculated as same thing, same cross-sectional area minus whatever height that surface of the liquid is currently at that time, whatever that is. And so we can sort of sub that back in. P initial. I guess we can just keep this as an equal sign. Cross-sectional area. Cross-sectional area. And well, cross-sectional areas cancel out, so we're given this as our relationship between, for the pressure at point 1 between its height. And so, well, we solve for every variable now. And so let's sort of simplify our Bernoulli's equation with everything that we've sort of figured out conceptually. And so the pressure initial just so happens to be atmospheric, right? Which is, well, the outside, the environment, which is external. So I'll label both as P external. Maybe not now, in a bit here. So we are solving for the velocity at point 2. So let's move everything to the side here. So this term was actually negative GH. So I'll put squared over 2 is equal to GH. I'll say plus, swap the signs. So it will be P1 minus P2 over rho. And that's about it. And then I'll sub in stuff here. And so this term becomes P initial times H minus HI over H minus H times 1 over rho minus P external. We can then do a common denominator. And so this will become P initial H minus HI minus P external times H minus H. And well, that becomes that. We can say that P initial, I'll erase it, is actually the P external. They are equal values, right? And then we can factor that out. And so I'll sort of write under this is, so then P external comes out, so that'll come out. So rho will be there, times, well, then it will be H minus HI minus this term, right? And so we will get H minus HI over H minus H minus 1. All right, and so then we can sub that back in. We'll get P over 2 squared. Oh, well, it will be, so multiply by 2 and then take the square root. So 2 times GH plus, we said this was the term inside now. So, oops. So this is just algebra, basically, from here on out. Minus 1. And we've now solved for the velocity coming out at point 2. And well, the original problem was solving for the height of the water as a function of time. And well, we're not quite at the height of the water yet. So we know that the flow rate, Q out, is equal to this velocity at point 2 times the area of the hole that is coming out. So now we have the volumetric flow rate, volumetric, right? So we can sort of relate that to time now. So we know that the volume within the container, the volume of the fluid, as it's changing, it changes with time, and it's going to be this. So the change in volume over time is going to be the flow rate out, which would be negative, right? Because it's decreasing. And well, we're getting closer to height, right? So how does the volume to height relate? Well, by the cross-sectional area. So we know that the volume is equal to the cross-sectional area of the container times the height. So subbing that in, we get the change in height, since the cross-sectional area is constant, is equal to, well, sub this in, negative the flow rate, volumetric flow rate. Divide the cross-sectional area of the container over, and oops, and I've ran out of lead. Good thing we finished right away, right now though. So this is our differential equation now for, hopefully it's seen on the phone cam, for our container, and which we'll solve now in collaboratory. And so I will see you guys over there. All right, so let's do this second part here, where we solve the problem numerically and we plot it. And then we'll be using this events feature to cut off our simulation when it actually reaches steady state. So let's start a new notebook here. I'll name this homework 2, part 1, I guess. Doesn't really matter. So let's do our usual imports. So we'll be using NumPy. We'll be using SciPy, if I can spell it right. SciPy.integrate, right? That's the main star of the show, because it has the tool that we're using to solve it, our initial value problem. We'll need plotly, subplots, imports, make subplots. I think that's it for our imports. So we'll do a bit of connecting here since I just made a new notebook. All right, so what do we do now? So solve IVP requires our function, a function, right, which that function will be our right-hand side that we had just derived earlier on our paper, right? The dh dt negative v2 times the area of the hole over the cross-sectional area, right? So we need to define a function that has that, so that solve IPP can do its thing with it. And so let's do that. So define a function, we'll just say right-hand side, and well, this requires time. That's just what it needs. That's the first input, and then we'll have a vector because this thing, solve IVP, is set up to solve for multiple equations at once. And well, ours, it only contains one variable that we're solving for, and so we can just pull that out of the vector instead of having to type initial number in that vector every single time in our equation. We can just pull it out as h. And so let's put v2, our velocity at point 2, into our code. And so that is the square root. I'll widen that out for now. 2 times, and then another parentheses, gh, g times h, plus p external over rho, and that's times, okay, so I'm gonna separate these parentheses a bit more. All right, so we'll have one set of parentheses here for h minus h initial, divided by another set of parentheses, h minus h, that'll be minus 1. All right, so I can sort of consolidate this down now. All right. All right, that looks right. All right, and then we want it to return, well, our function, right? So it will be negative v2 times the area of the hole divided by the cross-sectional area. And that's it. Now we can sort of put in all our givens. So g is equal to 9.81 meters per second squared. P external is equal to 101.325 pascals. Oh. We have rho being 1 e to the 3 kilograms per meter cubed. We have h being 1 meter. Let me just check that real quick. 1 meter. We have the initial being 0.9 meters. Check that as well real quick. 0.9. Yep. Then we have the area of the hole being 0.001 meters squared, 0.001. And then we have the cross-sectional area being equal to 1 meter squared, I believe. Yep, 1 meter squared. So that should cover all of that. So if we put in just some random value, so 0 doesn't really matter, and then some height, let's say 0.9, its initial. I have a float somewhere. Oh, right. So this should be entered in as a vector because it's expecting a vector. All right. And so we get negative. So then that value right there would be how our height is changing. So it's decreasing by 0.004 meters at that time. All right. So now that we know it's working, we can sort of now start to use solve IVP to solve it. Right. So it requires our function, which is the right-hand side, some time span, which I'll do from 0 to t. I know I haven't defined t yet, so let's do that. So t will be, to make sure it works, let's do 4 seconds. So then requires some initial value, which we'll do as hi, right? And then a method, which we'll do as radau. And then we want the dense output to be set as true because we want the solution of this thing. Okay, I forgot to, so when using solve IVP, when you put a vector into the function, it expects it to return as a vector as well. So since we're only returning one value here, we can do it as a list. And so there we go. Now it works. So looking at this, since I set the dense output to true, we are given the solution, the function, I guess you could say, that will spit out heights for whatever time we put in. And so that's what we'll be using to solve, well, that's what we'll be using to plot our solution, right? The relationship between height and time. And well, we'll soon find out here that this isn't actually fully, our resulting plot won't be correct. And so let's store this into a variable. I'll just do sol. And so to pull out the solution, we'll just do sol.sol, and then we'll pull out that attribute. All right, so to plot now, we'll need a time for plotting purposes. So we'll set that up. So that variable will be for plotting purposes. So we'll do np.linspace to linearly space out our x-axes. So we'll go from 0 to our time, and then we'll do 500 spaces, 500 points. So that should work. And so let's get to making our plot. So we'll do figure. This variable will be our make subplots. We'll do fig dot add scatter, and then we'll have our x values being the time plotted, our y values. Okay, so one thing real quick, I probably shouldn't delete it. So sol dot sol, and let's put in a test time real quick. So let's do at 1 second. So you can see it returns an array. And since it returns an array, we won't be able to plot that, right? Because it's not a value. Some other restrictions within this add scatter, right? And so we want that value. So instead of doing sol.sol at t plot, so instead of trying to plot an array which wouldn't work, right? We'll pull out that value. So it will work. And so if we do that, boom, we get our figure. And to consolidate this, I'll do update layout. I'll make the width and height equal. So width equals 600, height equals 600. And then we'll also do the template is equal to plot the dark. All right, and now it looks a lot better. And so you might be asking, why did I say, why does it look wrong? Why is our plot wrong? So let me extend this simulation time to 10 seconds. And, well, boom, our solution goes wrong. And so it says that we contain an infinity of some sort, or not a number, and well, how could that be happening? So let's look at our function for velocity. And well, usually the issue comes about because of a square root. Usually it could be a square rooting a negative or something like that, which is the case for this. So our denominator here, as h decreases, it increases, right? So this whole term here, since this is just a number, it becomes smaller and smaller, resulting in this entire parentheses becoming more and more negative. And so because we're running it for such a long time, this becomes a negative enough to where it overcomes this positive value and eventually square rooting a negative. And so sort of a fix to that would be to take the absolute value of the term inside, right? So I'll do that. It works now. And then we try to plot this, and all of a sudden it goes beyond steady state. And well, that should not happen, right? And so what do we do now? Well, this brings us back to this last portion of the homework statement where we use the events feature. So we know that the simulation should stop when the velocity equals 0, which is steady state for the system, right? So how do we make use of this events feature? So this event feature is where we make a function. Basically, we make a function, sort of mirrors the same setup as our right-hand side for solve IVP, because it requires it to be set up that way, right? And so this event feature will sort of look out during solve IVP. It'll look out for the events that you put in, so the functions that you put in, right? And well, when a function achieves 0, or well, a function that you denote as an event, when that function reaches 0, it'll do whatever you set it up to do. And so for our cases, we'll set it up to where the simulation stops when that function hits 0. And so what function are we sort of looking out for when it hits 0? Well, it will be inside that square root, right? We don't want it to be negative. Go negative. So we stop it when that value inside the square root hits 0. And so let's do that. So we have that. We can just bring this over. We don't even need the absolute value at this point. We just need the term that could even go 0, and we'll return that. So make sure I don't have an extra parentheses or anything. All right. And so then we put that into our solve IVP as events, and we stuff it in as a list, or an array, I mean, list or array. And since this could take in multiple events, that's why we set it up as a, well, it would be an array if there were multiple events, but since we're only doing one event, we can put it as a list, or, well, vector, a singular vector. And so it'll be our v event. And so if we just look at our solution now, we see that we have our time events here. It shows the time now when that value hits 0. So then that's when it hits steady state. And then in turn, which is when we'll want to stop our simulation and stop our graph. And so let's make sure our simulation actually stops right there. So we'll have to add the termination attribute to this. So our velocity events dot terminal will be set to true. Now it'll stop at that time. So now we want this time to be our end instead of just our simulation time. So we'll swap that out for sol.t events attribute, right? And then we'll see here that it's an array within an array. So we want the first value within the outer array, which is the array. And then we want that first value within that array. So then we'll have, we'll grab two first values, so to say. So that works out. So we have our new updated t-plot. And so now it stops whenever it hits steady state, which was at 4.56 seconds. And the height only goes down by 0.01 meters. And so now we can sort of fiddle with our givens. And this whole solve IVP and our events will stop it when it hits steady state. And so there you go. That is the end of part 1 here. Thank you.